1 2 1 2. Yes. Okay. Good. Oh, that's on. I don't know if anyone else noticed, but the waiting scene had my microphone live, and I hadn't realized that. So you got to hear my little mic check before I started to make sure that my little meters on my streaming software was were going. I can't remember now. Now that it's happened, I can't remember if I just said anything random while we were in that 1 minute of streaming before I start the actual lecture. Um, I was freestyle rapping about what I was going to lecture about to test the microphone and get myself warmed up to talk about programming this morning earlier, but I'm not going to do that on camera because my freestyle rapping days are over. They were very short. Uh, okay, so we can all hear me, which is a good start to the lecture for today. Let's kick it off with what we talked about last week and what we're going to talk about today. Um, People are laughing about the freestyle rapping thing. No, there were no genuine freestyle rapping days. Okay. I used to call myself MC Mchi because that was funny and it also kind of rhymes, but it's also not that great a rhyme. So, like this, it's comedy rap. Anyway, we're not going to continue on that line of thinking. So, what did we look at last week? Uh, Last week we covered two particular things. Um, oh no, maybe in the break I will do something. Because it will take me like an hour in the background of lecturing to actually come up with maybe only 2 or 3 lines that actually rhyme with each other. So, last week we had a look at what COMP1511 was as a subject. If you're worried about any of the details about what we're doing, so just like how do labs work, what marks do I need to pass the subject, and all other little things like that, they will be in the very first lecture, but also in the course outline in great detail if you need to have a look at it there. And then we looked at C as a programming language. So we learned a whole lot about C, about beginning C as a programming language. So we saw some of the basic syntax, which is things like how to set up a program, the hash include, using the int main void line as the starter for the curly brackets, which is where our actual code instructions go. And so you would have seen now after your tutorials and labs that the first the first programs we've made have certain things that are like nearly always the same in them. So if there are everything that's inside the curly brackets is going to be run line by line from top to bottom. And then we saw a few things we could do, like printf and scanf, which is going to give information to our user or take information from the user, and that's all going to happen in the Linux terminal window. We learnt about variables, so we learnt about how our computer stores information, and we learnt about a bunch of operators that can work with numbers, a bunch of relational operators, which is asking questions about the relationship between numbers. Oh my god, I should not have said anything about rapping. Man, I shouldn't have been rapping too much, because now you got me crapping that if I don't produce some content, you'll all... Nothing rhymes with content that has anything to do with leave the channel. Anyway, okay, that's enough. Logical operators were things that would take true-false statements and be able to decide between true-false statements if a certain combination of them made sense. And then if and else statements is our way of, for the first time, having our programs not necessarily run exactly the same one every time you run the program. So now with if and else statements, we can ask questions about what the program knows. So as the program's going line by line through its code, at certain points it will stop and it'll say, okay, what do I know about something? And if I know something, I will either take one fork or another with what we're doing. We're actually today not adding any new programming concepts because we've got lots of programming concepts as it is. But oh my god, I wasn't really rapping. Yeah, MCMG in the house, keeping it real. Anyway, keeping it real in programming, because programming is very real, and we're gonna do a lot of work with this. This is very weird. I thought that in my 6th iteration of COMP1511 that I wouldn't necessarily introduce anything new, but now I've probably got a theme that I'm gonna have to freestyle rap through this whole thing. Okay. So what we're going to do is we're going to use all of the tools that we looked at last week, but we're going to get a bit more complex with them. So last time it was take input and just check whether the input adding up met a certain number or not. This time we're going to think about what kind of problems could arise with a program like that, and what kind of solutions could we use to solve those problems. And so I want to talk a bit today about generic problem solving, about how we take things that may or may not be working exactly the way we want them to, and how we fiddle around with lots of different ideas to solve problems. One of the interesting things about programming is that you can create a program that achieves a result reasonably easily. So it's not that hard to make some code that does something. And it's very easy to then test it immediately and then decide whether or not it's doing what you need it to do, and then rewrite it. We're in a very, very particular field of engineering with our ability to do this. Because if you look at someone like civil engineering, who they would do things like build a bridge, and they would expect that the bridge can hold a certain amount of weight, or it can weather certain weather conditions. The way they have to test those things is either to build scale models or run simulations and things like that, and it's very, very hard. So you can't just put a bridge out in the wild and say, oh, it collapsed under a certain weight of vehicles on it. I guess that didn't work. Let's rewrite it and try it again. Yeah, Tom's mentioning about whether a bridge can weather the weather, and that is totally in the back of my head. I was like, I need to follow that up with another rap line, and now you've got me disrupting the flow of my own lecture because every line I say now, there's a little like piece in the back of my head that says I should say another line that rhymes with that line. So this is going to get awkward. All right, I'm going to continue with the lecture. So one of the beautiful things about programming is that we can actually solve our problems in a very test-driven way, where we can just keep testing things and say, does it work or doesn't it work? Rather than having to 100% know when we're creating something that it's going to work before we fiddle around with it. Oh no. Chat's just full of freestyle rap now. I find that text chat's really good for freestyle rap because you've got plenty of time to think about your line. Okay, so we're going to talk a little bit about problem solvings, and we're going to bring back the dice checker from last week. So I'm going to have the dice checker, and we're going to add to it. So as William was asking there, are we adding RNG to the saving throw checker? We're not necessarily adding a random number generator. I do mention it later, but it's not a random number generator. But 2 people asked last week, I forgot who it was, sorry. It's hard to remember everyone's names. But 2 people asked last week about what do we do if the input to the dice checker doesn't match what we expect. So if we don't get a value between 1 and 6. We're going to have a look at that today. We're going to have a look at some of the things we can do for certain kinds of inputs that aren't correct. And I'm going to extend that example into different ways that we can look at solving that problem. So let's have a quick recap, because I think it's good, because it's been 4 days? It's been 4 days since we last look at we last look at all the programming concepts that I dropped. I'm saying I dropped programming concepts on Friday last week, and so we want to just have a quick run through all of these before we start using them again. Um, the um, the way that we think of variables is part of how we were splitting um, the way that our computer does everything into two kind of parts. One being the thinking part, and the other being the remembering part. So one part of the computer we think of as processing information, and the other part of the computer we think of as storing information. And the variables are the first thing that we have done so far in storing things. So this is literally your computer grabbing part of your memory. So the memory is like, when we talk about RAM in a computer and the running memory, this is us actually using that and saying, all right, for an integer, I would like 32 bits worth of that. So 32 little ones and zeros that we can use, and a double is 64 of them. And the integer is storing whole numbers only, whereas the double can store numbers with decimal points in them. When we're using the variables, try to choose a name that makes the variable meaningful to us, and so we can remember it. This is something that's easy for the moment because we've only got one or two variables, but as we get into much more complex programs, we're going to be using sort of, I don't know, we could get up to like 20 or 30 of these things at a time. So having a name that tells it apart from the others and reminds us what its purpose is very useful. They are also called variables because we can change the value as we go. So we can keep a running value of something. We can have a variable that has no value in the beginning, but waits until the user types something in, and then we'll read that value into the variable. That's the example for the dice values that we had last week. Or we can have values that say start at a certain value and then they count upwards to other values as we do things with them. We're going to get more into this as we start to get more complicated programming concepts going on. All right. So we also had reading and writing to the terminal. So this was printf was one of the very first things that we did. Printf and scanf both come from using the hash include standard input output. So stdio.h is the standard input output library, and it gives us access to these functions. I'm going to go into more detail about exactly what functions are later, but for the moment we can think of them as giving us access to someone else's code. So someone else who wrote part of the C library, which is where we get standard input output from, has written these functions that say, okay, when someone says printf, we find the Linux terminal that this program is running in, and we put these letters in the terminal so that people can see what's going on. I wonder, there's a couple of questions in there. Tom, I'm going to let you answer the questions if you're there. If not, I will just pause at the end of a slide and then talk about some of them. So when we're working with both printf and scanf, yeah, cool. When we're working with printf and scanf, we have these % symbols. They're technically called format strings, which say that information will have a particular kind of syntax and layout. So a decimal, D for decimal integer, works with the integers, and it says a whole number. So it says any kind of whole number, it will be able to read or write. %lf says long floating point number. This one says if you have a double, so you've got the 64-bit floating point number, this will be able to print out that number, and people will be able to see that. We can read and write with those. Scanf is a partner to printf where it uses the same kind of format, but instead of writing something to the terminal, it takes in whatever the user's typing in the terminal and then brings that back. I always find it really funny when I'm doing typing because I try to do the idea of typing on the screen here, even though my keyboard's down here, but if I mime typing on my keyboard here, you can't see anything happening, so I do it up here in the air. Okay, so that will give us the ability to send information to and from the terminal. Then we had a bunch of stuff that we could do with maths to be able to just work with the numbers. And this isn't just working with the numbers. We could see this as a similar thing to algebra in a sense, that we'll be working with variables, and when we put a variable name in the place of a number, our computer, when it does this maths processing, is going to read the value of the variable rather than the idea of the memory that the variable's in or something like that. It will say, okay, if you want to add two variables together, we're going to read whatever values are stored in those variables and use them. So, I mean, if you've done any algebra with A, B, C's and things like that, this should be reasonably self-explanatory. The maths, I think, is something that is as close as it gets to programming not trying to reinvent the wheel and just saying this is going to be the same as the kind of maths that we would have if we were writing it on paper and then calculating it by hand. We can use brackets as well, just like normal maths. The one thing that I mentioned, but we didn't go into any detail with, is the modulus operator, where if we have a division between integers, we actually don't even need the division itself. We can use the modulus between two numbers to say, if these two were to be divided, what would be the remainder if one was divided into the other? We're going to have a look at that more today because I want to actually use some modulus because we've used a lot of the other stuff and I think a lot of the other maths is self-explanatory, but modulus is less so. So what we're going to do today is actually use that in one of our potential solutions to the problem that we have, and that way we're going to see what it is and how it works. What I'm going to do really with a lot of these things is like slowly go through and open up some of the details of how they work as we're working on things. Okay, the other operators we were using are these relational and logical operators. So these were the ability to ask questions about values. So for us to take some variables and say, is something greater or less than something else? Or are these two variables equal? Or is this variable equal to a number? That kind of thing. All of these, if we put a number on either side of them, the computer will look at that, it will process that by looking at the things on either side of the operator, and then it'll say, okay, that whole chunk there will get transformed into a 1 or a 0, depending on whether it thinks that statement is true or not. So if I have the double equals, so remember, single equals is our way to set a value. So single equals is like saying, here is a variable, and I want to make this variable equal to this number. So it's very different from the mathematical equals. Right? Whereas this double equals here is like a question, where it says, I'm going to put two things, one on either side of this double equals, and this thing is going to become 1 if those things are the same. But it's going to become 0 if those things are different. So this double equals is actually closer to what we think of as a mathematical equals. Just checking. Tom's answering all the questions there, so that's cool. All right. Logical operators are nearly like, if you ask these questions, you can combine multiples of these questions with the logical operators. That's not the only thing they can do. They can do other things, but generally, the logical operators are going to work on having 0 to 1 values on either side of them. So having true-false values on either side of them. Remember that the concept of true and false does not actually exist in C. So we might say words like true and false because they're very convenient for us as humans. And I know that people may have worked with other programming languages that have explicitly true and false in them. C doesn't do that. C is very, very pure in what it does. So everything that C does is closer to the concept of bits, which only have zeros and ones. So the way that true-false works in C is that false is a value of 0 for a number, and true is actually any value other than 0 for that number. So we can consider something to be true if it's anything other than false. And that way, no matter what an integer is, for example, we could get a result out of these true-false operators. We might show some of these today, actually. I think I'm pretty sure we will, of combining some of these together, and we'll show how the logical operators connect things together. Okay, little spoiler here from last week. I gave you one of the possible challenges last week if you wanted to do it. This was just a lecture challenge, so it's not like the lab challenge that gets the extra mark. So I'm happy to just kind of talk about this one. Was doing the branching control of a program we did a success and a failure. So we had a success if something was greater than or equal to, here it's actually greater than, and otherwise we had a failure. And I said, one possible challenge is, can you do a success and a tie and a failure? And so this is actually that challenge completed here, where we have 3 possibilities for every value that we could have. A genuine success, a tie, which is kind of a success, and then a failure. And so this shows us how we can use an if, and we say, okay, if not this, but something else, that's the else. So the else, if this one fails, else, then we check another condition. So what we're saying is, do we succeed? If we don't succeed, did we tie exactly? And then we could go into here. Otherwise, if we didn't strictly succeed or tie, then the value must have been a failure. So we can do this kind of branch and control of a program that can step through one after the other and check all the different possibilities of the outcomes that we could have, and we can say that so long as we finish with an else, we can guarantee that one of these possibilities will run every time we run the program. So this chain of if, else, and we can have multiple of these else ifs in here, means that our program's going to go through these one at a time and check them, and anytime one of them is true, that's the one that's going to get run. So that way we can kind of do a checklist. We can say, okay, let's go through all these things and see which one is the one that we're going to use. What are we talking about there? Oh, people are discussing some of the details here. I'm gonna let chat. I'm gonna let you talk in chat. I'll go to chat when there's time for me to actually look at what's going on. So I'll keep going. But I think Tom's answering most of your questions there. Okay. So on to, let me just move my face out of the way, the little meme here. Onto what I wanted to talk about a little bit today, which is problems and solutions. So one of the things that we want to think about when we're nearly doing any kind of programming, there's always a problem and we're always looking for a solution. So generally, in the easiest way we can think of this is the problem that you're trying to solve is the question that you're trying to answer in the lab. It's always going to get more subtle than that, because a lot of the time when you're trying to solve a problem in the lab, what you're going to see is it needs to be broken down into parts. And that's something we're actually going to do, and something that we're going to do quite regularly is every time I say, let's do something. So today we're going to add some nuance to the dice checker. We're going to think about what are the ramifications and how things are going to happen. The big question that's always going to be on our minds is, what is the problem? So this might be the question in a lab has some subtleties to it that we need to think about, some problems we need to solve. Or we can hit a different kind of problem where we can say, I have been coding for a while now, and the program that I'm writing does not run correctly. And so that is our problem. And so we can think about lots of different kinds of problems. And one of the most important things that we can do, and this is a very, very common programming issue, is that figuring out what you're actually trying to do is kind of important, and it's very important to think about the problem the whole time you're doing that. So the common thing that happens is we will start programming and we'll say, oh, this is really cool. I could do some really cool code. I can think up some really cool ideas for stuff that I can do. And then you just start writing code, and you write a whole lot of code, and it's like, oh, this is a lot of fun. It's really interesting. Look at me, I'm creating stuff. And then when you get to the end of it, you go back and you say, oh, what sent us off in this direction? And it was like, oh, we had a problem to solve. And since we were solving that particular problem, we sort of forgot what the problem was, and then we went off and did something else. And then we come back and we say, oh, did we actually solve that problem? It's like, no, we've got this wonderful code though. We wrote all this really interesting, wonderful code, except it didn't solve the problem, so we're not sure where we are now. So a couple of things that are handy when we're writing code for a purpose is every time we write a bit of code, we ask, is this helping us towards our goals or not? Is this bringing us back to solving the problem that we're trying to solve? The other thing that I was going to talk about here is actually figuring out how to solve the problem involves having a look at the problem and saying, a lot of problems when we start with them, they're large. They feel insurmountable. They're big things where you say, I can't just think up exactly what code I'm going to write for this. So often it's a matter of saying, let's break this down into its parts and let's solve each part one at a time. When we start building programs that are bigger than what we've done so far, we'll do this every time. So we'll say, this is the big problem, and here are the small parts that are going to go into solving that big problem. So it's good to see each one of those parts and say, does this help solve the problem? Yes, it does. It goes in. Does this help solve the problem? No, it doesn't actually help solve the problem. Let's think about that more carefully. We may not need to use that solution. So this is something that I've kind of mentioned now, but we're going to be seeing it a lot more. And basically every time I write a piece of code, what we're going to do is going to break it down into its parts and then see how we can make sure that each piece of this that we're creating is going to help with solving things. So let me just move my face back out of the way. What I'd like us all to get to, and this is something that you don't have to use exactly. This is not a procedure that is, it's not like a program or the syntax of writing C, where if you're not exactly perfect on this, it's not going to work. But I wanted to give you something which is the idea that if we always follow this kind of procedure, we should at least have an initial approach to every possible problem that we're going to get to. So these are the steps that I might take. First thing to do is figure out what's wrong. That was that question I said, what is the problem? Or what are we being asked to do? So we're being asked to create something, or if we're being asked to create some code, then we need to kind of have a clear idea about what it is that that code is going to do. Then we go, okay, what are our options? So this might be a situation where we've written a bunch of code and it's not working properly, and we think, okay, what we have to do is we have to change our code. And we need to figure out which parts of this code we need to change. Sometimes we don't have any code yet, and then we're thinking, what do we know about code? What's our toolbox? So at the moment in our toolbox, we have things like if and else statements. We have the ability to print to the terminal or scan from the terminal. So we know that there are certain things we're capable of doing at the moment with programs, and we say those are our options, which means we can use those options in combinations with each other, and there are many things that we could do that might solve the problem. So given that we have many options of what to do, we can say, let's have a look at those different options. I propose option A, which is to do something or other. We're going to do this in reality in the second half of the lecture today. But so I say, okay, I've got an idea about something that I want to do. The thing I want to do then is feed that back into point one of figuring out what the problem was. If we knew what the problem was, then we can ask, how well does this particular option that we have solve the problem? And then we can also ask, how do we actually make that work? So I could say that my option is some really, really complicated structure of code. And so I don't need to just figure out whether it solves the problem. I need to figure out how to piece all these code segments together so that they actually match and they actually can build and work. Sometimes solutions to problems will even fall over at this point because we say the code is so difficult to write that maybe this isn't worth it. Maybe there's another way around the problem. Maybe we need to assess a different option. After we've looked at a few of these, we will hit a point where we say, okay, we're ready. If we're ready, it means we're ready to actually start typing in code into the computer and trying one of these options and seeing whether it works. So this is something that I want to put into your heads as early as we can at this stage in week 2 that programming isn't about typing code into the computer. I mean, it literally is to a certain extent. But a great deal of programming is thinking carefully about what you're going to do before you start typing code into the computer. Because the second you start typing code into the computer, the second you get caught in a particular framework of how things are done. So we will be teaching you the programming language called C this term. And so if the first thing that you do in your problem solving is to start typing into C into your text editor, you will end up with a very, very kind of C specific solution to a problem where you'll just start running C techniques and hoping they're going to approach the problem. But if you think very carefully about what you're going to do beforehand, then what you'll do is you will approach your C programming by saying, I have a solution to a problem. I have thought through the solution to a problem. Now, when I'm typing code into the computer, the only thing that I'm thinking about is how to translate my problem solution into the C programming language. So then you only have to wrestle with, okay, what is correct C? Which techniques in C are we using? But you won't have to also at the same time wrestle with, is the technique that I'm using actually going to solve the problem or not? So there's a lot of work that we do. And when we're working in the computing industry, this is the kind of thing that we used to do is like, I've had times where we would spend sort of 2 to 3 weeks whiteboarding something before we touch code at all. That's a reasonably complex level, but it's still often fairly worth doing, because we could get to the point where we would spend 2 or 3 weeks literally on whiteboards in the office figuring out exactly what we're going to do, and then between the group of us we would spend 1 day coding, and we'd have like a release candidate for something because we'd thought so carefully about things beforehand that the actual like day-to-day sort of programming of it was not as difficult because we'd thought about how it worked. The next thing we need to do in this process here is to figure out whether it actually did work or not. So we've gone to this point where we've thought about the problem we're going to solve, we've thought about how we're going to solve it, we've tried something, and then we say, did that actually work? Because that's actually a reasonably difficult thing to figure out, okay? So it could have solved the problem, but it could have solved it in a bad way, or it could have solved the problem only for a certain subset of all the possibilities that might happen. But it doesn't matter entirely whether the solution that we tried definitely worked or not. Anything that we've attempted is probably going to give us some useful information, either about the problem itself or about our code and how it relates to the problem. So we say, okay, did it work or not? Let's have a look. Let's gain some information. Well, after we've gained some information, we feed back up into here again, and this actually loops, is we can go back here and say, okay, how well did that work? Does that now tell us more information about our other options? And does that lead us to which other option we could try? So lots of cool stuff like that in this process, where if you follow this, you can just sort of keep yourself on a path. And I think that's one of the interesting things, is that so long as we believe that eventually there is a solution to the problem, and that we have a process that we're going to follow to step through to find that solution, we'll probably get there. And I think that's one of the key things about problem solving, is that there's always a point in every problem where you look at it and you go, I can't solve this, I can't do this. And the second you switch off like that, it takes you ages to get back into the flow of solving things. Whereas if you've got this thing, you go, oh no, just follow the steps one after the other. It takes a bit of the brain drain out of trying to solve the problem by saying, okay, if we only follow the steps, we'll probably get there. So you can follow the steps and say, all right, I only need to do significant thinking in some of these subpoints in here. Otherwise, I can just follow these steps and write some stuff down, and then I'll work my way through difficult problems. Okay, I'm going to move my face out of the way of the images here. So I've just put some random images of dice here for the fun of it. Let's go back to the dice checker. So we, last time, we had a program that was able to take input from the user and it was able to add together the user's two dice values and report back whether that total was had met or not a target value. And we're going to narrow down to one possible problem. And the cool thing is, like, a couple of people did ask about this problem. So, just going to grab some dice. Got my... trying to show these to the camera without dropping. We've got my dice here. So, we were relying on the user to roll the dice and then just type in the number for the dice. But what if the user enters incorrect values? And we're actually going to limit even the incorrect values because we don't have enough programming yet to really deal with all the possible incorrect values. But we're just going to look at the user is still typing in integers, so we're not worried about if the user is going to type in letters or, you know, an entire sentence explaining why their character should succeed at this test without rolling the dice. I think arguments between your dungeon master and your players are things to be worked out on a game level rather than at this program's level. But we're still thinking that if we were rolling two six-sided dice, or as you can see, there are many other kinds of possible dice, but if we were rolling two dice, what if the user gives us a value that's outside even the possible range of those dice to roll? So that's definitely something we would consider a problem, and we have to think about how would we go about dealing with that. So, actually, before I get into that code there, let me hop into VLab here. So I just logged on this earlier, and I'll move my face out of the way over there. So what I'm going to do is I'm going to start from the dice checker as we had it last week. And so in order to do that, I'm going to I just wanted to show you some of the stuff that I would do in Linux to move some files around, create some folders and stuff like that. So I've done ls. Actually, I just did it there, but anyway. This listing shows me everything that's in the current directory. My prompt here is also showing me which directory I'm in, so that's pretty handy. So I'm in my COMP1511 directory, and I see Lecture 1 and Lecture 2 directories, which I made last time, which were... so I'm just organizing everything. I think it's nicer to have my files organized so I can find things more easily by just jumping to particular lecture directories. So I'm going to make a new one. So mkdir make directory, and if I do a listing now, I can see lecture 03. Now I said we're starting from the dice checker that we had at the end of lecture 2, and we're continuing on in lecture 3. I don't want to edit the one in lecture 2 because I want to keep that as the kind of final point we're at that lecture. So I'm going to make a copy of that, and I'm going to copy that into lecture 3. So if I was to do that here, I would do something like this: dicecheck.c, copy, and then go upper level, lecture 3, and then paste here. But what I want to do is teach you a bit about how things are happening in the command line interface here. So I'm going to copy, which is cp, and I'm going to say go into the lecture 2 directory. The slash says we've opened that directory and now we're inside it. And I'm going to do dice check. I'm going to press tab here, which is going to auto-complete this file name. And it auto-completed as far as it could go until there were different file names. One thing that you can do here, which is cool, is you press tab a couple more times, and it will show you all the different file options that could be auto-completed from that word dice check. And so I can say, okay, dicecheck.c is the one I want. So dicecheck.c, so that is the thing that I'm copying from, and then I say what I'm copying to, and I say the lecture 03 directory. When I press enter here, it's going to do a copy from the file dicecheck.c into the lecture 3 directory. So now I need to go into the lecture 3 directory to see whether I got what I wanted. So to change directory, to go into another directory, is cd, and I go into lecture 3. I go in there and I see dicecheck.c is here. So I know that now I'm in my COMP1511 lecture 3 directory, and I know based on the fact that I did this copy command from before, this dicecheck.c should be the exact file that used to be in my lecture 2 directory. But because I did a copy, I didn't do a move, I did a copy, the lecturer 2 directory still has the other version of that. So if we were to look at this here in the context of the kind of file management systems you're used to, lecture 2 still has dicecheck.c, lecture 3 now has a copy of dicecheck.c. So now I can edit the lecture 3 one safely without having changed the old one. Ian's asking, what does the tilde signify? So if I do this, cd tilde, it goes to my home directory. My home directory is this one. What that will do is it will remove all of the stuff that you don't need to know about. So all of this stuff here are the actual CSE servers and file structure that says this is how we allocate a working space for a student or a staff member. So mine's staff member, so mine doesn't have a ZID, it has my name instead. And then everything that I have access to is from here onwards, in a sense. So if I do a listing in here, we have from 19T1 through to the current one. The current one I don't name as the current term usually. So these are my backups of everything I did in previous COMP1511, which is the same as if I had done a directory listing on this first line here when I was in my home directory. So if I do cd comp1511, it's there. A lot of people will do this when they're working just because it makes your prompt smaller and a little bit easier to read. So here I'm in comp1511, and then go into my lecture 3 directory. So I have this habit of every time I do cd, I do an ls afterwards to see what's there. That's the same as saying that every time I open one of these, I get to see all the files that are in there. So that's an instinct. You don't have to do it because you kind of know where you are already from doing cd, but I tend to do it because I just like to see everything that's there. Okay, so gedit dicecheck.c, and remember that we put an and after this that allows this terminal to keep running while the gedit window is running. If we don't put that and, then this terminal stops and it waits for gedit to run and finish. And what that will mean is we won't be able to do any terminal commands in here, which is slightly annoying, which is why we do this and. I'm not going to go too deep into the details of why that works. When you reach a certain point, when we're happier with what we've done with programming and we want to do harder stuff, we'll learn about what's known as threading, where we have more than one program running at the same time. But I'll just drop that hint. I'm not going to go any deeper into that. Okay, so here we have the Dice Checker lecture demo. Let me, actually, I'll see where I'm up to in my slides. Let's think about what might happen. Actually, did I? No. Okay, I'm gonna actually run a demo of this first before I talk about it. Okay, so dice checkers like this, and we roll our dice. I'm gonna roll some dice now. We're gonna run the dice checker. So I rolled a 4 and a 1 there. Oh, in order to run this, so as we can see here, I only have the dicecheck.c file in my directory. So I have a program written by a human. It's not yet computer readable, so I'm going to run DCC, and DCC is going to take what I've written in my dicecheck.c file, and then it's going to translate into something that we can basically run, and the computer will go through the instructions in that and actually make the program work. So DCC is the thing that transforms, doesn't transform actually because this stays, but it translates this into basically a series of zeros and ones that the computer is going to read precisely and run the program itself. Tab completing again, so I don't know if you can tell how fast that appeared. I don't actually type that fast. I tab complete sometimes so that the file appears there. So dicecheck.c, and then I'm going to call my program dicecheck, This is going to think for a moment. It's actually thinking for longer than it normally would there. Okay. If I do my ls, I now have created this output file. So the -o says output file. This, every DCC command is always going to need to read a C file. When we get deeper into this, we're actually going to be able to read multiple C files, but for the moment, just one C file at a time. So we're going to read this C file. We're going to create this output file, which is this. Now, dice check here is the program that we can run. So // says run a program in the directory I'm currently in, and we call that dice check, which is going to access this program and make it run. So like last week, we've got the values of 2 dice. So I rolled this a second ago. I got a 4 and a 1. So I rolled a 4 and I rolled a 1, and the total rolled was 5, and the dice check failed because I was below the secret number. Lots of questions there, but I think Tom's answering that. Oh, right. Tom's clarifying for me that someone was asking about the, not the tilde here, which is, so I just went off on a different tangent, but the tilde at the end of the file. So it was, I'll show you a trick. ... goes up 1 level. So ... will go to COMP1511. So if I want to go to the lecture 2 directory, I can say ... to go up 1 and then down again into the lecture 2 directory. I think it was this one that what people are asking about. This is a backup. So gedit itself will save multiple copies of your file in case you make a mistake and you delete one of them. So I often just let these things hang around because I feel like it's always nice to have a second copy of the file. Every time I save it, it's going to save both of these. So in case I do something wrong and I delete something, hopefully I'll still have this other one there. Or even I make some changes and I think, oh, I want to roll that back a little. Maybe this will be the thing to roll back to. But you know, it's just the same as that. In fact, let's open it and have a look. So we see here that we've opened the tilde version of the file, and because it's C tilde, it doesn't know what colors to put on everything, because it doesn't know that this is actually the C programming language. It says you've got a file that's C with a tilde, so don't know what that is. That's a file extension I don't really know anything about, but here's all the text, and it's the same text as our program, which means that it's a backup for us if we need it. Okay, back to the actual code itself. Let's go back to lecture 3. Let's say, for example, I'm going to roll my dice again. I'm just going to make sure that this is something that fails. So I got a 2 and a 1. So a 2 and a 1 I'm pretty sure is going to fail this dice check. But I'm being sneaky. I'm being a sneaky human being. And I put a 2 in there and I think, oh, you know, I would much prefer to succeed in this dice check than fail. So while no one else is looking, I'm just going to put this number in here. Like, what's that over there? Look over there. Oh, I succeeded. Great. I succeeded my dice check, and I didn't cheat at all. I did very much cheat. I have put in a number that was impossible to roll on that die, yet my dice check programming is telling me that my dice check was successful. So, yeah, right? So I'm going to go to the casino with my dice check program, and I'm going to try to convince them that yes, I did roll that number, and they need to give me a whole lot of money. Someone was asking about the CD. I was just showing a trick here where ... goes up a directory. So if I'm in lecture 2 and I want to go to lecture 3, I can go up a directory which goes back to 1511, and then into lecture 3 from 1511. So CD was change directory, and this was a trick to go up and then down into another directory. I could have, if I wanted to, just CD ... and then would have gone to 1511, and then CD lecture 3, I would have gone there, but I combined them together like this. David's asking what would happen if I said I rolled a letter. We have weird issues in the way that scanf and C work for rolling a letter. We're not prepared to deal with that just yet. We will eventually, but with the code we have right now, if we put in a letter, we will have a very big issue with this program. This program's not even going to be able to run if we put a letter in. I'm immediately tempted to explain that, but I know the explanation has to go into levels of detail that are beyond what I want to deliver in this lecture, because we're only in the third lecture of our series. Having said that, stick around after the end. I think after the end of the lecture today, in question time, I can talk about details like that, where I've got time to talk about it, and I don't necessarily want to talk about it now, though. Okay, so the issue that we have with dice check. Now, go back to our problem solving process. The issue I have with dice check is I have a problem that users can type in any number they want. Let me go back to my slides. So here is the same kind of code. It's not going to be exactly the same because I like to write the code in the lectures live rather than copying down what's in the slides. So it won't be exactly the same, but it's very, very similar. We ask the user for their input and then we scan the input into the variables. Here we have the input range. So if we were using six-sided dice, and as we've seen in the previous slides, six-sided dice are not the only kinds of dice, but they're the ones we're most used to, so I'm going to talk about using them mostly. We're only expecting inputs in this range of 1 to 6. This isn't even to scale, this number line. If this was to scale, this little red bar of the number line of the ints 1 to 6 would be a tiny, tiny blip. It would be like maybe 1 pixel sized here, compared to the gigantic size of the possibility of integers between, I think it was -2 trillion and +2 trillion, roughly, here, which means that all of our range of possible inputs that we would accept as integers via scanf is way, way bigger than the bits that we want here. So we need to have our program capable of saying, I will only deal with inputs within this range, and I will only work with inputs within this range. And this now we're starting to get a really clear idea of what our problem is. Our problem is that inputs could be all of this, but what we really want is only these. So let's keep to that idea that the purpose of this program is to figure out whether someone using some physical randomizer can test whether a number was above a certain other number, and within that randomizer we should have everything only within this range, right? So now we're thinking really, really clearly about what our problem is, and then we're going to think, how can we deal with the things that are outside that range? So first thing that we're going to do is we're going to say, can we identify whether something is or inside that range? And we've got a bunch of tools that we've used to do this. That's the actual code there, but let's hop into our code and have a look at what we're going to do. I'm just going to close that one. So I have here asked for input and read in that input. Then immediately I'm going to say check whether this input is in the valid range. So what I can do now is anything that's going to be a check. One of the nice things is if we think about things in human language, anytime we're checking something or asking something, or we say to ourselves, is this something? That's nearly always going to be an if statement. Because what we're saying is we don't know for sure about something, but we want to find out some information. So how do we find out some information? We ask a question. At the moment, the if statement is the only question we know how to ask in programming, so let's ask that question. I mean, strangely enough, because this example was built specifically for you to learn about these things, it is the right question to ask. So here's an if statement. It doesn't have anything in it yet, but I've completed my brackets. So as I said last week, I like to complete my brackets before I write code, and that way my syntax is more likely to be correct. So if I did something like this, okay, if ask a question and then close that brackets and then open this, and then we write some more code. Yeah, this is code, it's not really code. I could go on and do other stuff and write some other code, and I may have forgotten to close those brackets. So what I like to do is to cleanly, without any of this other stuff, just do this first. So I know that no matter what happens, this if statement is now complete, and it can run even if there's nothing in it. I forget whether it can run with nothing in these brackets here, but I'm pretty sure it can. Okay, so what is the question? The question is, did we just then read as input a number that could have been created with this die? So a number between 1 and 6. So I would say that number has to be greater than or equal to 1. So I can say, is die 1 greater than or equal to 1? And I also want to say, is die 1 less than or equal to 6? And I want both of those conditions to be true. So if I want both of those conditions to be true, I need to say and, because and says both sides of this have to be true for us to accept it. So is it less than or equal to 1? Oh, sorry, is it greater than or equal to 1? And is it also less than or equal to 6? If I do this, I am definitely going to be able to see that this would be true. So what I do like to do here often is comment inside my if statements to say what I'm doing. So here is die is inside valid range. I'm going to be clear on that. And then else die roll was invalid. So if it's between 1 and 6 inclusive, which is why we have the greater than or equals to, less than or equals to, it is valid. Otherwise, it's invalid. I want to show one other thing, because this is one of the points where maths and code are slightly different. So if I comment out that line, so I can comment out a line to say to the compiler, don't read this line. I'm going to write something different. So you may be tempted to do something like this. Mathematically, this is a correct statement. So this is saying, is 1 less than or equal to die 1, which is also less than or equal to 6? If we look at this from a mathematical context, it makes perfect sense to us. If we look at this in a programming context, things will get weird, because the way that the program will run this is it will say that you have given me something and a less than or equals to, and then something on the other side of the less than or equals to. And then what we will do is we will process both sides until they end up as a number. So what we're going to get here, we'll get 1 less than or equal to, and then this side will get processed, which is die 1 less than or equal to 6. So if the die 1 was less than or equal to 6, it'll be like a 1. And then if the die 1 was greater than or equal to 6, it'll be a 0. So it won't necessarily get you the result you're looking for when it processes that. I'm pretty sure that if we were to do this in DCC, DCC might even actually tell us that there's a problem there. So what we want to do is, if we have kind of more than one question to ask at the time, we want to ask those questions separately. So I'm going to get rid of that and say, this is the code that we want. We had a question there. Rosie's asking, how do we know that the integers go from -2 to the 31 and not -2 to the 31 plus 1 and 2 to the 31? It's just a matter of, that is how the integers have been set out in C. So they've been specifically set out in the C programming language that 0 is a positive number. So it's kind of like we've got 2 to the 31 positive numbers and 2 to the 31 negative numbers, and 0 gets counted as one of the positive numbers. Even though 0 is neither positive or negative, just the way that works in C is they said, okay, we're just going to allow 0 to be part of the positive numbers, which means that there's one less positive number. There's not really a matter of how we know that works, other than that's the way someone decided that the integers would be set up in C, and so we just use it. Oh, Miguel's saying that works in Python. Yeah, I'm not surprised. Uh, every now and then we're going to see the difference that Python was created somewhere around 20 years later than C, and so they try to make a few things more human friendly than in C. Tom saying Python has magic. Yeah. Okay. All right. Tom and Shrey are both here, so they're answering lots of questions. But I think we're pretty close to break time anyway. All right. Let me just. Actually, I think this might be. Yeah, that's the one more thing before the break. Okay. So one thing that I do want to think about here is this 1 and 6. So as I said a second ago, the 6-sided die might not be the only kind of dice we're using. I mean, if we were actually doing this for Dungeons and Dragons, it should have been a single 20-sided die, not 2 6-sided dice. I did 2 6-sided dice because I wanted to actually show you adding numbers together. But this 6 isn't guaranteed. If we're going to do a dice checker that's going to be able to work with lots of different kinds of dice, we need to be able to set up different kinds of dice. So what I want to do actually is add some hash-defined constants here. Oops, got to be able to spell first. And I would like to say what the minimum value and the maximum value of each die could be. This could be really interesting because we could actually make up abstract dice that aren't exactly the same as normal dice. So I could have, for starters though, I'll say the minimum value of the die is 1. I think I just did exactly the same typo there for hash define. And the max value of the die is 6. The cool thing about this, we're on a computer, we're not really tied 100% to physical dice. I could say, okay, the minimum value is 3 and the maximum value is 8. I could still potentially do something like that. I don't always know if I start screwing with these numbers, whether that's going to cause a problem later on in my code. But I do know that if I give these a 1 and a 6 and I say, is the die 1 greater than or equal to the minimum value and less than or equal to the maximum value, this line now suddenly makes even more sense than before. Because we can actually read this in English now, and we say die 1 greater than or equal to the minimum value, die 1 less than or equal to the maximum value. You can nearly, we're not quite there, but you could nearly read this without knowing anything about C, because you just read the English words and you know a bit about maths. You're not sure what this is, you're not sure what all the brackets and stuff are, but you have an idea that we're checking for the values within the min and max value. And the cool thing about this now is if I want to change this to a 10-sided die, I just change the maximum value to 10, and we may be reusing the min and max values later on in the code. So hash defines are really nice like that. The constants allow us to say this is something that will be going through the use of the program, all through the program. The minimum value will always be 1 and the maximum value will always be 6. And then if I want to run the program again, I can say this time run it for 10-sided dice, but when I change this, it will be for the whole program. So this is not a variable. The size of the dice is not variable during the program running. It's a constant and it stays that way. So this will give us the ability to check whether something is or isn't in the range. So at the moment we can get to the point where we can sort of identify identify the inputs that are correct or not correct. And we've got these here. I think I've already spoken about this. Yes. I'm covering up some of the text there, but it's reasonably obvious what that was. Okay. Let's go on break here because we've hit midday, so we should have a break. So it's 12:04 p.m. Oh, actually, I just wanted to talk a little about dice. Sometimes in the breaks, I will just do random trivia like this. The idea of using physical stuff to randomize things is actually really, really old. So the earliest that we've found, which is not necessarily the earliest that existed, But games made by the Egyptians had flat sticks where you could throw it and it would land on one side or the other, kind of like flipping a coin. Senet is thought to be one of the oldest board games in existence. So we're talking about predating chess by several thousand years, I think. The first six-sided dice that have been found were in Iran a few thousand years later than that. Nowadays, dice range generally between 4 and 20-sided dice, but there are lots of others that people are using. We can also simulate three-sided dice with halving a six-sided dice and rounding up, sorry. Or even a two-sided dice if you flip a coin, that kind of thing. We're not looking at random number generation at this point of the course, but we will at least mention it later. So we're still relying on our user to create the random number by typing something in. All right, let's, it's 12:05. Let's come back at 10 past 12, and we're going to go into the code. We're going to go into some problem solving. We're going to look at different possibilities for solving these problems. Oh, I should probably say, while we're here, the lecturer in charge has been here the whole time. This is Chicken. She's just been sitting behind me on my chair the whole lecture today. So this is one of those rare moments where she will actually come and say hi. All right, let's go and break. Be back in 5. Did I say I was going to freestyle rap in the break? Lecture's not back on, by the way. I'm just going to freestyle rap in the break. Yo, this is Chicken. She's my cat. If she was cooler, she'd be wearing a hat. We tried that once around Christmas time, but she threw it away like it was only a dime. That wasn't really a very good rhyme. But you know, it's okay because we're in break time. In today's episode of Dear Lecturer, please don't give up your day job because you're not very good at other stuff. I'm just going to go back to... Actually, I'll just move the camera again. Just go back to showing Chicken. She's pretty chill at the moment. We're still on break, by the way. We're not back in the lecture just yet. But when the clock hits 10 past 12, then we will... People are being far, far nicer than then that wrap justified. Having said that, cute cat, which is more fun. All right. I can't believe that's going to be part of Term 3, 2020. We're going to remember that Term 3, 2020 was the freestyle rap term. You know what's going to happen. What's going to happen, and it's my fault, but also I'm blaming all of you for helping this along, is that I'm going to end up, like, your content is going to get a certain amount of time spent on whether the content is good, and then the whether I can make some of the delivery of the lectures rhyme is going to end up taking up a significant amount of the content prep time for this course. Oh, well, it's summer. That's it. I'm going to go through and I'm going to change the way the assignments work for this term. And what we're going to do is we're going to do a whole bunch of work on different rap. I actually did want to do this at one point, is do a whole thing about educating people about the golden age of rap and hip hop, which I think would be a lot of fun. But forcing it on people who are supposed to be learning about programming is probably not the best idea. Okay, let's get back into it. We've had our break, which is not the usual break, but a bit more than that. So let's continue. What are our options? So here we have the capability to decide whether a role was valid or not. Now we need to decide what we're going to do if the role is valid. If the role is valid, we can probably just continue as we were. So we nearly want to flip this question and say, if it's valid, then we're going to do something weird. If it's invalid, we're going to do something weird. If it is valid, we're just going to continue with the program. So I might flip this if-else statement into just an if statement that says, is this input incorrect? So I'm going to get rid of that else, and I'm going to say die role was invalid. So if it's invalid, I'm saying is die 1 less than the minimum value, or is die 1 greater than the maximum value? So you can see now, in flipping this the other way around, I've been able to show you the other operator. So if it's less than the minimum value, it's outside the range. If we, did I just, hang on a second, I just delete that by accident. I could just Control Z there to undo that. When we look back here, there's two spaces that this could be outside the range. It can be lower than the 1 to 6, or it can be higher than the 1 to 6. If it's in either of those, it's incorrect. Translating that graphical concept into code goes like this. Is the value for die 1 less than the minimum value that we've said, so less than 1? That would then say that this if statement needed to run, so the die roll is invalid. Or is the die roll higher than the max value? Die roll also is invalid for those. So either one of those can be true, and then we'd end up in this if statement. So if the die roll is invalid, we need to do something about it. I just went back and saw chat, and there's a disturbing amount of chat about how we can incorporate freestyle rapping into COMP1511. I'm going to go back to looking at my code screen and not look at chat for a while. Okay, so we have the ability to check whether the die roll is invalid, but now we need to decide what we want to do. So in the problem-solving process, now we are here. Oops. I forget that I can't select stuff on slides. Okay, so what are our options? And we're going to assess each of those options. So what we're going to do is we're going to do this step by step, where we're going to actually go through a bunch of these, implement them, and see how well they work. So we have several options. First option is panic. This may be a human instinct. This may be something that we could do. I mean, even worse than panic is do nothing. So where we are right now is do nothing. where the humans can just type in whatever numbers they want to in this program and nothing goes wrong. It just goes, yeah, whatever. We're just going to add 10,000 as if you rolled 10,000 on the dice. So another option actually doing something is to panic, which is to say we don't know what to do with these inputs that we've given. However, there are other things that we can do that are to take some kind of action. The first one we could do is let's reject the input and end the program. So we could just say, you've cheated, we're out. You know, we give up. We're not dealing with the fact that you cheated. Actually, the question there someone said was, where is it? Does C even allow you to panic? It doesn't really. So the first real option here is to reject the input and end the program, and we can do that reasonably easily. So we'll have a look at how that works. But we could also do other things. We could tell the user that the input was incorrect. We could maybe remind them of what the correct input was so that next time they do it correctly. I mean, maybe letting them know that we can see that they're trying to cheat is handy. But there's other things we could do. We could actually correct the input. So we could actually say that you typed in a number that was outside the range. I'm going to make that into a number that's inside the range. We're going to look at a couple of different ways we can do that. We could ask for new input. We could say, go back and do that again. What you did was incorrect, do that again. At the moment, with the code that we have as of today, if we're only using exactly what I've taught you so far, the ask for new input is very cumbersome. However, on Friday, I will start teaching you how to repeat running the same code, and then this one will become an option. So I've put it in here just because I wanted to talk about it. It's not an option we're looking at today. We're going to look at these three today and assess some of the possibilities that we have there. So, reject the input. We can flat out reject the input, and we can do that by ending the program early. So, remember here, I was talking about the return keyword and how the return keyword was going to end our programs. The return keyword doesn't technically end the entire program. It ends this main function. The main function just so happens to be the entire program. But when we learn more about functions, we're going to have more functions than just the main function, and we'll be able to return out of different things without ending everything. That's just detail for later, by the way. But if we want to, we could say here, return. We could say this program is ending here. And what I might do at this point is I might say something like, this program's ending, but it's not ending the way it's supposed to. So return 0 said, I have no problems. That's the way I like to think of return 0. Return 0 says, I have no problems. If I have problems, let's say I've got 99 problems, but the correct dice roll was not one of them, I could return the error code 99. So in terms of like those kinds of error codes, you would have seen certain error codes with web pages. Like 404 means it doesn't exist. 400 means I think you don't have the authority, the security to open it. So if we wanted to, we could set up our program to say, okay, different kinds of return values mean different things. So, 400's bad request. 500 is the not secure. I can't remember. This is a reason why these number codes are not used as much as they used to. And they all have translations now into human language. But either way, what we're doing here is saying that we are returning something other than 0, which means that the program did not finish correctly. So if I save this and run this, so just bear in mind what I'm doing here at the moment is I've only edited die 1, not die 2. So I haven't put any security on die 2 yet. What we'll do is we'll come to a decent solution and then we'll put that on die 2. But we're going to do all our testing with die 1 for the moment. So let's have a look at what happens now if I compile this so that it can run, and then I give a value that's outside of the correct range. So first thing, I'm going to have to DCC that. Dicecheck.c, and I'm going to name my program dicecheck. Compilation was okay. I mean, I haven't changed that much code, so the likelihood of me adding errors in is reasonably small for the moment. Also, you'd hope that I don't necessarily create errors immediately on code when I've prepared it in advance and I'm showing it to you. When we get deeper into things, I'm going to start throwing errors into code intentionally, because I think that you're going to see a lot of code with errors, and you're going to want to know how to get around those errors and how to fix them. I've got an entire lecture on that we're going to do at some point in time, but not necessarily today. We've got other things to think about. Okay. So I run dice check now, and so let's go for something that that's outside the range, so we can see whether this new addition to the program that we've had is working. So let's say that someone else rolls the dice, and I'm their friend, because this is how I treat my friends. And I go, yeah, sure, buddy, because I think it'd be funnier if they fail this check than they pass it. So I put in a negative 100, which means they pretty much guaranteed to fail. And then the dice check program just disappears, right? If this happens, then one of the issues with this is that, yes, the program was able to, by virtue of this, it was able to see that the thing I did was invalid, and then it was able to deal with it by just shutting down. The downside to this is that I have no idea what happened here. Did the program crash? Did it stop working? Is there something else going on? Or is it just kind of, is it rejecting me? So the thing that I think that this does, so let's go back to the problem solving thing. We picked an option to try, and we tried it. It did work. So it refused to give an answer when the input was invalid. But it didn't work that well. I don't know if the program failed. I don't know if the program was trying to tell me something. All I know is the program ended. So it's really kind of abrupt what happened there. Did I have... Yeah, I did have a slide on that. I knew I had a slide on that somewhere. So is this a good way to reject input? And if we are going through a program and say it's a lot bigger than this, say we've got like 10,000 lines of C code, and all that happens is our program just stops, then we don't necessarily know what caused that problem. We're not always that sure where we were up to in the code or anything like that. And so we hit this point where we're like, okay, it ended very abruptly. It didn't tell us why anything was happening, and we don't know why. So can we improve on this solution to the problem? And we probably can improve on this solution in a really simple way with the simple tools that we have. So why don't we report the failure instead? So why don't we at least tell the user, this is where you went wrong and this is the problem? So let's try adding that now. Here, and we say, okay, we're not just going to leave, we're going to let you know what went wrong first. So I'm going to say die1 was not a valid value. I'll put a /n on the end just to be nice to move the prompt down afterwards. Okay, so we'll save this and run this. So the change is subtle. Programmatically, I have not really done anything that makes the program run in a very significantly different way. But what I have done here is potentially worked very, very much towards the idea that this is something that's going to be used by a human. And if it's going to be used by a human, then we should actually use some kind of human communication method. Because this return 1's not actually coming through to the human. Like, we don't see the 1 in the terminal. We don't see any report here that says that this program finished differently with the return 1 to the return 0. So if we want to tell the person something, we really want to print something to the terminal. So let's try that. First thing we need to do, compile it, and then run it. So as you can see here, me using my up and down keys on my keyboard allows me to go back through my commands. So now that I'm in this kind of cycle of testing and running, I'm going to be using my DCC and my run command multiple times, and so it's nice and easy for me to use my up and down keys to get back to them without having to type everything in again. I run this now, and let's do this again to check for the invalid value and see whether it gets us the right kind of errors. So this time, my friend says, "Get off the computer. I'm sick of you typing negative numbers in. I want to pass the test this time." So they cheat in the opposite direction. And the dice checker this time says, "Die 1 was not a valid value." So it's actually saying to our user, there's something wrong here. It's giving us a reason why it was ending, and that helps us a bit. So that gets us closer to a kind of a solution that we might want to use, something that might actually help us. We can do better. Strangely enough, the lecturer has set up the examples so that every solution that he creates is kind of okay but not great, and then he can show us a slightly better one as he steps through the lecture. Yes, like, you know, of course. All right. I can do better without even changing this that much. I can do better by not just telling people that they were wrong. This is like educational theory. It's like, I'm never just going to tell you you're wrong. This would be really funny. Okay, so if I go into chat now and I just look at everyone's questions and I say, no, 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 no. That's not really a good way to teach people. It's also not that good a way to have a program run. So let's add some information. So let's say not just that the input was incorrect, but let's give people some information about how to make it correct, or give people some information about what ranges would have worked better. So I could say the input for that die that they gave was outside of the range that we have, and the program will exit. So this gives the person a whole lot more information. I'm actually going to improve on this bit here. So let's say not just that was invalid, we're going to say, I'm just going to delete all of this actually. Die 1 that was outside the range of this to this. I'm going to need to split this onto another line. I'm going to tab that in. Program will. I'm gonna have to fix this up. Program will exit now. All right. So one of the issues, is a good time to talk about this. You'll notice this vertical line in your gedit window. So let me just go back to how I would do this if I wasn't really thinking about stuff. Program will exit now. I have 3% Ds. If I have 3% Ds in here, I need 3 variables after a comma here that are in the right order for those. So the first one was whatever die 1 was rolled. So I know that's the variable die 1. The second one was the first number in the range. So we're going to use the min value for that one. And then the last one, the third one, was the maximum value. So we're going to use the max value for that one. And that line finishes. Okay, so this vertical line here is a helper. The helper there tells us that things are going to get harder to read the further we go past this line. I will usually try to never go past that particular line. So the reason being is that when we read code, we tend to read it vertically. So we'll tend to be looking at the left edge of the code and looking at things. The downside of that is this one here doesn't really allow us to see which variables are part of that print statement because it's so far out of our view. On my editor, I mean, I've got my font pretty big so that I can do this on streaming and lag doesn't cause you to be unable to read everything. This, I mean, like, it's completely out of view, but it's going to be Latin in pretty much any editor, which means it's going to be really hard to know what's happening. We're going to scan down here as we're looking. We're just going to be reading this thing, and it's hard to see what's happening. So what we will often want to do with this is split this over multiple lines. So one reasonably simple way we can do this is we can use the same bracketing system as we were doing otherwise, where we indent this and then we have this bracket close in a matching kind of setup to that opening bracket, in the same way that this bracket opens and closes like that. So that'll get us an extra line, and then we can split stuff down into multiple lines. So I can do something like this. The text goes on one line and the variables go on the other lines. If I need multiple lines here, I can do that also. I'm not sure if this is going to work. Yeah. I think if I needed to do that, I would have to do multiple print statements. I think this is okay, though. I've gone over that, but only a tiny bit. Maybe that's okay for now. All right. So this is like, we're going to go into more detail about how to restructure your code to be really readable, but I thought I'd at least show you this once. So this is going to now, going back to the actual function of the program, this is still just one printf statement, which means that this is the text that goes on the screen, and this variable matches up with the first one, second variable matches with the second one, third variable matches up with the third one. All of these for the moment are integers, which is why they all have the %d symbol. If one of them was a double, we'd use the LF symbol here instead. The beauty of what's happening now is my program will now be reporting useful information to my user about what they could have done better with their die roll and what would have worked, and also to inform them that the program is exiting intentionally. A couple of questions there. Oh, Rosie's asking me what would happen if we press enter between the quotation marks of the printf. I think it won't compile, but let's see, because I kind of want to. So I'm going to do this and test it. I think there's a lot of things like this where you'll have a really good question, and but we'll often still give the same answer. It's like, just try it, because it's worth seeing what you can and can't do. If you don't kind of figure out what C will and won't accept, you're kind of, it's like you're in a room where you could move into all these different spaces, but instead you stand in this little spot. Because you're not sure where the walls are. So it's worth trying. So we're going to try this now, and we're going to compile this and see whether that accepts that second line. New warning, missing terminating double quotes. So it's saying that line had to be finished on that line. Error, expected this expression, double quotes, and it's saying program will exit now is incorrect. So it's not letting me split that over the line. What I might do if I was going to split that over two lines like this is I'm just going to take this bit of text, just move it there for the moment. And so I've got this first printf statement, because we can actually do multiple printf statements in a row. And if we don't put a /n after this printf statement, this next printf statement that I'm about to make will follow directly after it. Oops. So this is going to have a similar effect, but now all of my stuff is well within that line of, like, this is like kind of this suggested line of readability. Once you get outside that line, things get harder to read. So now I have two printf statements. One of them, which is this one that says the die's outside of this range, and these are the values that the die and the range. And this one is a really simple one that just says, okay, the program's out. I'm a head out, I'm out of here. So let's run this again and see whether the information we're getting is a little bit more useful or not. Compile again. We're not getting any warnings or errors this time, which is good. We would prefer our programs not to have warnings and errors, because most of the time they're not going to run if they've got any of those things. There's going to be some serious issues with them if DCC needs to talk to you about it. Okay, so run that this time, and let's type in a value that is incorrect. So let's say someone rolled a 10-sided die by accident, and it was supposed to be a 6-sided die, and they rolled a 9, and they thought that they were being genuine, but it was the wrong die for the check. So it says, die 1 that you have rolled, 9, was outside the range of 1 to 6. Program will exit now. So what we now have is a significant improvement over the previous possible solutions that we had. First solution was just to exit, and we didn't know what was going on. Second solution was to say, you've done something wrong. So that was beginning to get to the point where we were giving useful information to our user. This current solution is saying to the user, this is exactly what you did here, the 9. This is exactly what we expected. This is our reaction. So that's quite good, because we're now giving a lot of information, and we're saying, if you want to try this again, if you want to run this again, you know exactly what you need to do next time, 1 to 6, and you know what I'm going to do if I don't like it. So there's a little bit better communication between our program and our user at this point. Oh, Shrey saying, yeah, we could use multi. Let's leave things as they are like this for the moment. Emmanuel saying you did 2 sets of quotes within the same printf and that worked. I've never actually tried that. I've always used a single set of quotes in a printf, but maybe that would work. So maybe you can put multiple sets of quotes on the lines. In fact, that also makes this lecture slide, because it's not actual code in the lecture slide, it's just me typing stuff in, that makes this potentially incorrect code on the slide. But all these things, it is worth testing them. It's worth playing around with them and seeing what C will and won't accept. Okay, now let us think about another option. Let's think about, instead of exiting, let's think about the idea that we want to have an answer no matter what. So we think that the dice check program is sort of trivial enough in what it's doing that we want an answer from it even if we give invalid input. Now, this is a question that will come about based on why you are writing your software. Different kinds of software have different things. So if, for example, I have written software to aid in medical diagnosis, so software that is going to take a series of inputs of like, are you coughing? Or do you have a headache? Or do you have a fever? It takes all these questions and it tries to diagnose whether you've got the common cold, the flu, or COVID, or something else based on the symptoms. I mean, COVID's not a good one. There's too many different symptoms we don't understand yet. Let's say the cold and the flu, we can kind of guess, and doctors will do this as humans. If we have a program that says, don't worry if the information is inaccurate, I'm going to give you an answer no matter what, that's probably not something we want to use in a medical diagnosis situation. Like, for a medical program, we're probably at a good point now where it says, input was invalid, I refuse to give a diagnosis. I am not just going to silently correct your input and say, I'm going to give you an answer to your question. However, when we're rolling dice, we understood that the input was a kind of a random input. So what if we just correct the input? So we ignore the fact that input was invalid, and we say, we're just going to do something with this input and make it work. So we've got 2 options here. One of them I'm going to show you quickly is the clamping option. Don't even know if we need to code this one. Oh, we will anyway, just because it's interesting coding maths to do it. And then we have modulus, which is the one that I want to show you, which is my elegant solution to this problem. Okay, so clamping is a common term that we'll use sometimes, both in maths and computer science, which is just to say that. Oh, hey, Ollie. Ollie's one of the tutors. I haven't modded you on this. Hang on a second. There you go. I gave you mod status, Ollie. Ollie's one of the other tutors, so he's dropping in to say hi. With clamping, what we can say is, let me go back to here. There are plenty of values we could receive that are higher than 6. There's plenty of values we could receive that are lower than 1. For any of the values that are outside the range, we just push them. We're just basically going to compress them back into the range. So anything higher than 6 becomes 6, anything lower than 1 becomes 1, and then the other numbers in between can be whatever they are. So basically, anytime I roll like 100 or 9 or 10, it's like, no, they're too high, but I'll just give you the highest value that we can possibly have. Anytime I do negative 100 or whatever, those are too low, but I will give you the lowest number that we have. So clamping is just going to squish everything into the range. And it looks a little bit like this. If it's below the minimum value, it becomes the minimum value. Or if it's higher than the maximum value, it becomes the maximum value. So where are we? Here. So now, instead of exiting, in fact, what we can do, I'm going to say code for rejecting input and exiting here. And I'm just going to comment this out. So it's still valid code that you could use if you wanted to. And so I'm going to leave it in there in the demo so it's still available for people to look at. And then I'm going to say clamping code here, which is going to say that if this was outside the range, we can just push it inside the range. We're going to leave this part in because I can say your die roll was invalid, but I'm still going to fix it. Previously, it was your die roll is invalid and I'm leaving, but I could say your die roll is invalid, I'm going to fix it. So I'm going to say if it was less than the minimum value, I'm going to say push it back up to the minimum value by setting it to the minimum value. Otherwise, if it is higher than the maximum value, squish it back down and set it to the maximum value. So what I have now, everyone's talking about loops. Don't worry, it's coming. Those of you who want to be able to do things over and over again in your code, looping code, we're going to talk about that on Friday. So what this clamping code does now is it guarantees that no matter what we type in, the program, once it goes down into the totals, will always have values between 1 and 6 to work with. So let's save this, compile it, and then run the program, which is the result of the compilation command. Now, if we have any value outside of the 1 to 6, we're going to end up with a correct value. So if I type in 10, and remember that the code we have written here for checking and correcting is only on the first die. So the second die is still just raw. So I'm gonna be honest about the second die. Good question there. Alan is asking, why was it a single equals and not a double equals? So double equals is a question. Single equals is an instruction. So what I've said here is I've asked a question. If it was lower, I give it an instruction to change the value of die 1 to the minimum value. So if it was lower than the minimum value, it becomes the minimum value. If it was higher than the maximum value, it becomes the maximum value. So here I'm not asking a question, I'm giving an instruction. So slightly different. So it tends to be that inside the curly brackets are instructions, and inside these normal brackets in the if statements are questions. So you get the question there, and then the answer, in a sense, there. Rosie, you can kind of say that. It's not 100% the case. So Rosie's saying, can I say that equals is used in statements, whereas double equals is used in expressions? You can nearly say that, because there's always an expression in here, which is like a question. And this, with the semicolon on the end, is a code statement, which is an instruction for doing something. So a lot of the time that's the case. However, sometimes you can put double equals in here, and you can actually use a single equals in here. It's just very risky. So I think that what you're saying is good. It's a good way to think about it. But there's also possibilities that you can do things in other ways. Okay, so looking at the clamping code, if I say 10, it's going to say 10 was outside the range of 1 to 6. And then please type in the value of second die. So me not having a /n there is making this look a little awkward, but it's okay. Please type in the value of the second die. I'm going to make the second die equal to 1. And the total rolled magically becomes 7. So if we were looking at this not knowing about the implementation that I had made before, this looks weird. Because it's like, how is 10 plus 1 equal to 7? But at least this line here gives us a little bit of information to say that die 1, which was 10, was outside the range of 1 to 6. The clamping, which says that I can only have values between 1 and 6, has pushed the 10 back down to 6. Let's show that with the other possible example. So I'm going to say -1. So I feel like my rolls are so bad all the time that they're -1. And the same thing, I'm going to get a report that that was an issue. Let me just say 1 again for the second die. Total rolled was 2 because my -1 got pushed back upwards to 1. So this is something that's going to make it so that we're always going to get values between 1 and 6. Now, it's definitely correcting the input. We're definitely ending up with something that works, but it's kind of like, is this a correct solution? Every solution we've had so far can be considered a correct solution, but they can all have different levels of how useful they are. And so this is where, the subtleties in problem solving are coming into it, where we may have solved the problem, but have we solved it in a way that does the best thing for us? Do each of these solutions and the way that they solve things, do they meet our needs of the initial program? So yes, clamping meets the needs, but it sort of means that the majority of times we're going to type in numbers, we're going to get 1s or 6s, and only occasionally are we going to get the 2, 3, 4, and 5. So it's a little bit, it's okay. But we have this downside as well of just correcting stuff without the user knowing, which leads to a certain level of confusion. So what we could do is we could actually come in here and say something along the lines of, before we do this clamping code, we're going to say, let me correct your value. And so at least then the program is saying that it's going to correct the value that was outside the range. A little bit more information there, that can be handy. But what I wanted to show you is another thing, which is to use modulus. And modulus will give us a different result that is interesting because it's no more correct than the clamping result. Anything that's correct is just a value inside the range of 1 to 6 that we're looking at. But modulus is going to give us something that will actually feel closer to the roll of a die. And the reason it can do this is it will give multiple different values depending on the input value. So let's look at this. If we mod 6 any number at all, it will give us a value from 0 to 5. I should put a caveat on that, it's not any number at all. If we mod negative numbers, we're going to get -0 to 5, which is going to cause us a few issues, but we're not going to worry about them too much for the moment. So, Any number mod 6 gives us that, which means that no matter what numbers we have 6 possible values, 0 through to 5. If we change that 0 to a 6, we get the range 1 through to 6. And that 1 through to 6 range is exactly the possibilities of numbers that we're looking for. And Girachand is giving us one possibility for that. So I could change the 0 to a 6, or I could add 1 to each of these numbers, and I would also get the range 1 to 6. So both of those is going to work. Let's, for the moment, I'm going to comment out the clamping code. Let me show you another commenting way. I did actually mention this in the commenting slides, but I'd never shown you this working. The /* here, between these two, everything between those two will be ignored by my compiler, so the computer will never read any of this. So I've got this way where I can comment out the lines individually, or if I've got lots of lines, it's easier to comment them all out like that. I'm going to leave all this stuff in the code so that you can use these later, and you can say, like, I don't want to delete the things for the different solutions. Okay. I'm going to say more. It's like putting a comment on something to say that it's code is not that useful because it's all code, right? But I'm going to say that these are different kinds of value correction that we're going to do. Okay, so assuming that if we're inside this if statement, then the roll was invalid, then what we're going to do is we're going to do some mod on it. So I'm going to say die1 is now equal to die1 mod 6. Not mod 6 though, because I don't want the number 6 to be in here, because what if I change the size of the dice? So instead of mod 6, it's going to be max value. Die1 mod max value is going to give us a result between 0 and 5, which means that I do need to convert that 0 to a 6. But what I might do, because Girachand's talking about it there, we're going to use Girachand's possible solution there. So this gives us the value 0 to 5. If I add 1 to that, I'm going to get the values 1 to 6. So now, no matter what value I type in here, I should get the values 1 through to 6. Although, as I said before, it's slightly different with negative numbers. So I don't know whether we'll look at that now or not. Yeah. Education says we have solved the code, but at what cost? Okay, so let's have a look at how this works. So I just want to show this running to show you what kind of results we're getting out of this. So die1 mod max value. So let me remind you exactly what's going on here. This is like a division, but it's not a division. So remember, if we divide two numbers, so we divide die1 by max value, so dividing a number by 6, we could get a remainder. So this is saying that the value of what's in these brackets here is the remainder if we divided die1 by the max value. So now die1 can be any astronomically high number. But all we're going to do is say what would be left if we divided by 6, which means we get the values 0 through to 5 as the remainders. We add 1 to that, we get the values 1 through 6. So let's save this, compile this and run it, and see what kind of correction we're getting on things. So let's say, for example, I'm going to go for my cheaty thing again and try to roll 100. I am going to get my computer reporting to me that 100 was outside the range 1 to 6, and it's correcting it for me. Maybe I could put some more information in here to say how it's correcting it, but, you know, we'll leave that as it is. I'm going to put a 1 in here for the value for the second die, and the total roll is 6. So what that's telling me is that there was a certain amount of remainder on the 100, and that remainder got converted into the number 5. So if we think about this, I think that the closest divisor, it would have been 96 with a remainder of 4, and so the mod would have given me 100 divided by 6 would be 96 with a remainder of 4, which means that this thing in the brackets here becomes the number 4. We added 1 to that to make it 5. 5 plus the value of the second die 1. Sorry, 5 plus the value of the second die 1 was 6. So that gave us a value that was inside the range of the dice that we're looking at. But the interesting thing about this is I can actually use my human input now as a sort of a random number generator. So if I was to run this again and type in a number which I am not really clear on how this divides by 6, it's actually going to do the division for me, and somewhere in there I'm going to get a what feels random to me of a number between 1 and 6. So I'm just going to put 1 in again for the second die, and it happened to be 5 again. So the remainder, when I divided this number by 6, happened to be 4. We added 1 to it to put it back into the range 1 to 6, and we happened to get a 5. I could run this again and type in a different number, and this time the total was 3, so my remainder must have been a 1, and then I added 1 to that here in the code. Yeah, so what I'm actually getting is the feeling of randomness here. Oh, I keep getting similar numbers, but anyway, it is still random. So something really interesting that I'm getting here, and this is not always the kind of solution that we might reach for different kinds of programs, but the fact that the original intention of the program was a randomness thing, I'm getting something that feels right to my user in terms of randomness. Ningting Zhang is saying, but if dice 1 is a negative number, the remainder is also negative. Yeah, so if we do this, and then a 1, I'm getting -2. So the remainder is negative. We can actually fix that if we want to. So we could do, let's do a simple check that is going to give us the right kind of values without us having to modify things too much. So I'm going to take my +1 away here and do a really simple if statement here. So I'm going to say die 1 has the possibility of being negative. So if die 1 is less than 0, die 1 was negative, make it positive. And we know that if it's already been modded, the negative value can only be within the range of -5 to 0. So if it's between -5 and 0, I can say die 1 is now equal to, so I'm changing the value of die 1. If I add the maximum value, that's going to make it into a positive number. So we could, and I can see people are coming up with other ideas here that we're using absolute value, which you definitely could do as well. That would work just as well, where what we could do is say, if it's negative, we reflect it to positive. And people are doing that manually here as well. So if it's less than 0, we can multiply it by the negative of itself, and then it would become positive. I just decided to do that in the simplest way possible with the least amount of maths, which is just, if it's less than negative, if you add the max value to it, it just pushes it to positive. So we're not reflecting it to positive, we're just pushing it up. And while we're dealing with values that we don't care that much of the integrity of the value, we can do lots of different things like this. So we've made it into the positive range. I'm going to do something cool here. Less than or equal to 0. We add max value. So now we deal with two situations. This thing could give us a 0 value, and if it's a 0 value, it ends up being plus max value, so the 0 now becomes 6, and anything that was negative also gets added the max value, so that everything gets pushed up in the range of 1 to 6. I'm pretty sure that's going to work, but we'll see. So now I don't have to do the +1 to shift everything into the positive range. So I've got the values 1 to 5. If it's a 0, it gets pushed up to 6. If it's any negative number, it gets pushed into the positive range. Jonathan's asking if I'm going to upload the code after this lecture. Definitely, because there's a lot of complicated code here. So let's compile this again. I'm having to press the up arrow lots of times there. And we'll run it. Now, you're not necessarily going to see what's happening here because we don't have much output saying what's happening. But now I should be able to type in a random number, and I got a value between 1 and 6. Let's do that again, but this time I can type in an arbitrary random number, and I still got a positive number out of that. So my modulus is able to give us a solution that is going to allow us to basically roll our face across the keyboard and get a die roll out of it. So we don't even need to use the dice anymore. We can just spam the numbers on our keyboard and we're going to get a randomized result. Okay, so there's some example code for modulus, but I think the code that we did in the lectures is even possibly better than that. Oh, so a couple of questions there. Anson saying, if the negative number is less than -7, adding 6 won't help. Yes, but note when I added 6. So I added 6 to the value after I'd modded it. So if it's after I've modded it, the remainder cannot be larger than the maximum value. So because I'm adding to it after I mod it, that's why it's getting a good value every time. Because this will have a range of -5 to +5. So anywhere in that range. So if it was negative, anything up to -5, so long as I add max value to it, is going to go back to a correct value. Yeah, I took out the +1 because I realized I didn't need it anymore because I could just add 6 to the 0 here. That's why I added the less than or equals to there. Anyway, we're pretty much out of time. We're actually just 1 minute over time. So we've looked at this a little bit here, that using the modulus means we will always get a value between 1 and 6. We don't shut down unexpectedly, and we still get this kind of randomish result. The cons are we're not necessarily letting people know that what they typed in wasn't correct. And we do have an idea that we're sort of overriding the user's expectations here. So we've got to watch out for little things like that. So, little things that I want to talk about, we have come up with many different possible solutions to this problem. I rushed through a few of them because some of them didn't need that much explanation. But we can think about what was the original purpose of the program and how we worked on it. Do we fail on incorrect data or do we fix it? A lot of the time we'd actually prefer to fail on incorrect data. But as we do more stuff like this, we're going to show you in assignments and things, we're going to say, this is correct data, this is incorrect data, this is the behavior you should have on correct data, this is what you should do with incorrect data. So we do need to still think about these kinds of things. Okay, so we've upgraded the dice checker with bits and pieces, and oh, actually no, that's just slides for all the code that we have. Okay, so what we did today is we have done more code, and we've added in a lot of other things to do with if statements. So we're chaining if statements together now, and we've done some really, really complicated stuff with modulus, but also we're just looking at some simple things here we can do with rejecting input or just pushing the input back into its range. So I really do need to wrap up here. So we've gone too long. So I will end the lecture here and we'll go into break mode, but I will be back as usual answering your questions afterwards. All right, thank you everybody. as the new lecturer in charge, I would like to ask all of you to send snacks. I have disposed of Mark, and I am now in charge of COMP1511. Anyway. I just thought that would be funny. Okay, I'm back and ready to talk questions and things. Girichand, I'm very sorry that you have to do this in a weird time zone. I'm sure you're not alone as well. I think other people are in awkward situations as well. But I'm glad that we at least have this tiny time slot that is not too early in the morning for people in China and not too late in the evening for people in the US, but it's kind of bad for both of you. And I think our friends in the subcontinent are even worse off. And I'm really sad that all of our international students don't actually get to come to Sydney, because it's quite a nice city, you know. It's like one of the major tourist destinations in the world, and it's really like part of the international student experience is also getting to be a tourist and a student at the same time. So I'm hoping that sometime during your degree as an international student, we will feel safe enough about the pandemic that we'll actually be able to visit. Not that I want people to be traveling when it's still unsafe, but hopefully soon. Yeah. Okay, so let us cat, yeah, chicken eating chicken. We named wait, Yurichan, you're a domestic student, but you happen to be in the US at the moment. Is that the deal? Did you get stuck there? That's unfortunate. But I mean, it's not like only a small percentage of the students are actually doing face-to-face tutorials anyway. Okay, let me open it up now because, as usual, I have dropped a large amount of beats and rhymes on you and code. Oh, maybe I can make the code rhyme. That would be really, really difficult. If anyone has any questions about the code that I wrote today, and I'm sure there are, because I know that there were a lot of questions in chat near the end there, and I hope that people were answering each other's questions and things like that. If anyone has any questions now, please put those questions into chat and I will be able to answer them. Right, okay, so you've been in the US for a couple of years, but you're an Australian citizen as such. So I guess it wouldn't be the same as what I was saying for the other international students, that it's like part being a student, part being a tourist. So for you, it would be like just coming home if you were going to do that. Chinmay is asking, what are the benefits of completing the challenge exercises? So in the labs, the challenge exercises can give you some bonus marks. Those bonus marks will apply to your lab component of the course. If you get 100% in everything else in the lab, the challenge exercises don't really change your marks as such. Having said that, if you happen to miss a lab or get less than full marks in another lab, the challenge exercises can make up for that. The other thing really is the challenge exercises are if you're hitting a point with a code where you're so happy with it and you're so happy with your understanding of everything and you want to just push things a little bit further, that's what the challenge exercises are for. Some of them are devious. Some of them, one of the challenge exercises later on in term, you'll know when you see it, is harder than I think either of the assignments. So it's thrown in there to see if anyone's interested in. It's nearly just to get you thinking about things more than we have any expectation you're going to be able to complete it. Only one person has ever actually completed it as one of the tutors. So, but it's good anyway because it's worth thinking about. Sometimes we want to see what the future of what we're doing is, even if we can't do it yet. Okay, so marks-wise, that's what they are. Thinking and learning-wise, that's also what they are. Okay, Kat's asking, could we try to put a decimal as one of our roles, even though they're meant to be an int? That's a good question. Let's try that. So, running the program. Let's try just giving us a correct answer so we can see clearly what's happening without the mod changing anything. So let's put 4.5 in as our first die. Oh, well. Okay. Let's have a look at what might have happened there. I thought this was going to do something different, which is, I think, one of the great things about this, is that often when I'm teaching, I have these assumptions of how programming works, and because I've lived the last sort of 20 years of coding with these assumptions, I don't test them. So what I thought was going to happen is it was going to drop the 0.5. It didn't drop the 0.5, but let me talk a bit about the subtleties of what's going on with scanf. So die 1 picked up 4. So it took the input as this whole line of text, and it said 4 is a number, and there's a full stop after that number, so I'm not going to deal with that. So it actually said that this is a full stop, not a decimal point. So it didn't read the whole number, because a %d is a decimal integer, and a dot is not part of a decimal integer. So it took 4, and it put 4 in die 1. What that did then was it left it left 0.5 in our input. So it's still in our input, and it just hasn't been processed yet. So the interesting thing about having the 0.5 in our input is the first bit of our input is a dot. So this is what happened. It went in here, scanned 4 into die 1. It skipped this because die 1 was inside the range, and it came here and it printed out, please type in the value of the second die, because we definitely saw that. Oh wait, please type in the value of the first die. Did it actually? No, it didn't actually print that out. That's fine. But what it did was it got to this scanf. I think the reason this didn't appear is because there's no new line, so it didn't actually make it to the terminal. Scanf here looked for a decimal integer for the second die. So this is subtleties of scanf that I said I was going to talk about anyway, so it's worth talking about here. Trying to read in a decimal integer when this is what's left in the input, because the first scanf only took the number 4, as you can see here, because that was a valid decimal integer, and then there was a dot afterward that was going to ignore. However, the dot is now the first thing in input. So die 2, what it's actually done here is it said, I'm looking for a number, and it didn't find a number. It found a dot instead of a number, so this thing just finishes and it moves on. Because it says there was input, but it was the wrong kind of input, so I will not put anything into this variable. So it's read this and said, I can't take a dot. So it has not done anything with die 2, which means die 2 here, as we created it, had no value. And then here, this has failed, so we have not given die 2 a value, and then it's moved on to here, and it's tried to add die 1 to die 2. And we can see here, this is the line in which it broke. And trying to add die 1 to die 2 when die 2 has no value means that we cannot put a value in total either, and so everything falls over from there on. So I think that was actually a really, really interesting question there, Kat, that our scanf is not capable of doing the things we talked about that integers could do, which is like they're going to ignore the decimal point and just use the value, which is I thought what it was going to do. But scanf was more specific than that. It's going to read those characters and say which of these match the pattern that I was looking for, and the pattern is decimal integer, not floating point integer, so not fractional. So sorry, floating point integer, not floating point number. So yeah, I think that was a really interesting question, and we can explore what scanf can and can't do. Strangely enough, this is the same thing that happens, question from earlier in the lecture, if we type in text instead of a number. Both scanfs will try to run, and when they run, they will just reject the input because it's not the right pattern. So if they reject the input, they will not have a value because they won't have written anything into die1 there. So the first one hasn't written anything into die1. And then we try to check it against something, but it didn't have a value, so it can't do anything. So that's why we're getting that kind of failure here. So scanf says, I will look at what's been typed in and I will try to grab something from it that makes sense to me. If I can't grab anything that makes sense to me, I will leave it there. Which is why we have two scanf functions running, and I only typed in one. But it didn't matter, it still ran both scanfs because there was something in input ready for it to read. Another thing that's interesting that we can do to look at this kind of side effects, ramifications of scanf, is I could do this. I type in a 1 and a 6 and press enter, and its total rolled is 7. So what's happened here is the first scanf has taken the 1, and then it's left a space and a 6 in the input. The space scanf does know how to ignore, and so then it's read the 6 as the second input. So even though I only typed in a number once and only pressed enter once, the two scanfs have gone, oh, I'll take the first one. The other one says, well, there's still something there, I'll take the second one. So there's a lot of little subtleties going on with how scanf works. You can see why I didn't put this in the lecture. I spent an hour talking about just the subtleties. So yeah, it's a weird thing where all of the input for the program is put in a buffer. So this is all the letters that have been put into the program. Scanf looks at the start of that and says, that's something I want, and it takes it. If it's not something that it wants, it leaves it there, assuming that we're going to have something else in our code that deals with it if it's not the right thing. So what I could do is I could have scanf looking for a number, scanf looking for a letter, scanf looking for a floating point number, and then I could have a sequence of inputs that are of different types. You know, when I said scanf looking for a letter, I haven't taught you how to do that yet, so don't worry about that. We'll look at that kind of thing later. Okay, so I think that was a good exploration into some of the things that we can do with scanf. So let me go back to questions. Isaac's wondering if everyone here is in their first term at UNSW. I actually assume not, Isaac. I know that a lot of people are. So we've got a mid-year intake kind of thing happening at the moment, but we've also got people who are in other degrees who have computing as part of their program, but they don't need it to necessarily progress through, so they can take it as a third term thing. Those of you who are in computing degrees have to do this subject first because it's the prereq for everything else. But those of you who are in other engineering disciplines, like I'm thinking like mechatronic or electrical engineering, a lot of the things that do a bit of computing but not that much, will do other subjects first, I think. Oh, there's a bunch of people who are saying it is their first term. Ningting Jiang's asking, how do I know how many spaces I need before each line of code? So the way that we do this indenting, so I am going to talk about this in great detail in another lecture when we're talking about code style and things. That'll be, I think I'm going to do that Tuesday next week. Don't quote me on that because the schedule is based on how I've written the lectures in the past, and I don't have it entirely memorized. Is usually this is 4 spaces. Different people will work in different ways. Different program languages will work in different ways. It's generally thought of as a kind of convention. The 4-space convention is reasonably normal, but I wouldn't say that it's the only way to do things. I've seen people use 2 spaces. And I've seen people use 3 spaces as well, and I've seen some people use 8 spaces to indent. So I think that 8's a little bit much, but you know, basically we will adhere to whatever standard that the group's using that we're programming with. So here in 1511 we use 4 spaces. Knowing when to put the spaces in is usually if something is contained in something else, then it'll go 4 spaces in. So pretty much all the code we're writing is 4 spaces in because our main is containing everything within its curly brackets. So this curly brackets here, ending in this curly brackets here, means that everything with 4 spaces in is inside these curly brackets. if I open another set of curly brackets, I go 4 spaces further in. So anything that's 8 spaces in is both inside the main and inside this if statement. So this if statement goes all the way down to here, and that's where it closes. The highlighting helps us see that. And we see that everything in there was indented 4 spaces, unless it was also inside something else. So this was inside something else, these if statements. This gets a bit messy because we've commented out, but we can see it here. Inside these if statements, we go a little bit further. And what that means is we can read this really easily when we're looking at it. We say, this if statement, everything inside this if statement is at this level of indentation. And then when it finishes, the bracket pushes it back to the previous level of indentation. And then any other code we'd write after this would be at the same level of indentation because it's inside this if statement, and it's also inside the main, so it's 2 levels in. So that's how we would decide how we're going to indent this. You can press the tab key to automatically go the 4 spaces. It'll still put 4 individual spaces in, but that's the quick way of doing it. Also, we're going to, usually whenever we press enter at the end of a line, it's going to automatically put us at a reasonable indentation for the next line. It's not always going to be correct. It's going to guess, but a lot of the time it's going to be correct. Lynn Ronkong is asking, will the weekly programming test be released during this week? We're actually not releasing the first one until Thursday next week. So the content that you are learning now, or actually the content that we learned last week about if statements and things like that, that we're doing in the tutorials and labs this week, will be tested next week. So it's kind of like week 1 content gets used in week 2 labs, tested in week 3 tests, so that we've got our 3-week cycle like that. Kat's asking, you're welcome. She was just thanking. Oh, sorry, I just gendered you automatically. I apologize if that was incorrect. Thanks for showing that. Just as well, if we put a space between 2 numbers as our input, would that give the first number as die 1 and second as die 2? Oh, I think I did that, right? I did that just as you were asking it. Yeah. Laura's asking, can we use constants and variables in a printf statement, or must we use %d to get the values? This is an interesting one, and we should look at this, because we've got one here that does this. Okay. %d was outside the range of %d to %d, and we had min value and max value. Now, an interesting thing to think about here is that the min value and the max value, when we do them as hash defines, they're going to come through here and do text replacement on things. So we could, instead of doing the pattern string there, we could do it like this. So let's just, I'm going to Control X, cut this, paste it there, cut that, paste it there. Now we see the potential issue in what we're doing, but let's see if this works. So I have put the right text for the hash define here. However, it's inside quotes. So let's find out. I'm going to compile and run this and find out whether it actually prints out the word min value because it's inside quotes, or whether it does the correct text replacement. My guess here, and I'm going on instinct here because I coded it and I put the min and max value outside of the quotes, is my guess is actually going to spell out all the letters min value and max value. But I do want to verify this. So I'm going to save it and run it and see what we get. Oh, I'm going to have to compile this first and then run it. So we need something outside the value so that we can see what's happening. So I'm just going to do 7 outside the value of 1 to 6. Okay. So the issue that we're getting is that these names are not noticed inside quotes. And so we can use a lot of words inside the quotes and a lot of names for things like variable names and stuff, which would potentially, if we thought of it as code, trigger access to variables and stuff, but because they're inside quotes, we can say what we want. So when we're talking to the humans, we can say what we want. So I can use keywords in here that otherwise wouldn't be allowed. So I could say something like main int double return. None of these things are going to have an effect on the program itself because they're inside the quotes, and we're allowed to say those words to the user. So that's why here we are not able to necessarily just dump those straight in. Cat has noticed the thing that I do sometimes where I refer to humans as if I'm not one of them. So robo lecturer, beep boop. Yeah. You don't know if I'm a robot or not. This could be a really, really good deep fake. Okay, so let's put that back to what it was, min value and max value. I think that that's all the code we need. I'm going to compile this again. Oh wait, program's still running. Oops. And all those up and down arrows I had caused issues to scanf. Alright, so we'll compile that again and run it just to make sure that I haven't broken anything there. Type of value outside the range. Yeah, okay, so it's corrected the value. Awesome. Yeah, this is a serious programming right there. Okay, I think that's everything. Last chance, if anyone has any other questions that they would like me to go through. I think those are some really good questions though, because what we got to see there was some of the subtleties of scanf, which we're going to go into later when we start using it in earnest. And also we looked at some of the potential issues with what goes inside the quotes and also constants and stuff like that. So, any other questions before I sign off? I'll give you a couple of seconds to type them in, because I know that the stream is a little bit delayed, where I think it's not actually that delayed. I've actually got really good latency on this stream where it's only a few seconds behind what I'm actually saying. Oh, also, I should just for the fun of it. Someone's been sitting right here on my mouse pad because the mouse pad's nice and soft and she likes to sit on it, and the vents for my laptop are just poking out, like the hot air's coming out there, so she just likes to sit here in the warmth. It's very cute. Okay, I'm going to assume that that is it for us for today because we're out of questions that people are asking. So goodbye from myself and the lecturer in charge, Chicken. Your tutorials and labs this week are going to be working on stuff like this. Maybe not as full-on complicated with modulus and everything as this, because it's going to be content based on last week, but there'll be a lot more practice with if and else statements and things like that. So we will see you on Friday. On Friday, I am going to introduce a new topic, which is looping, and that's our ability to then repeat code. There's a lot of cool stuff in that as well. All right, goodbye all. Goodbye. She didn't like me doing that. All right, see everyone later.